monosaccharides will lap back on themselves and form rings, something like what a cycloalkane looks like. Additionally, these rings will then attach to each other, and when there are two attached to each other, it is called a disaccharide. Let's start with seeing how do the monosaccharides look when they form a ring. So far, we've been looking at the monosaccharides in an open chain form, like what we have on the left there with the glucose. You can see it is an aldehyde on the top, and then we have our hydroxyl groups in a right, left, right, right form. The bottom hydroxyl group that identifies it as being D-glucose, you can see the oxygen is a little brown on it. What happens is this will come around and attach itself to the carbon that's in the carbonyl. When it attaches itself to the carbon that's in the carbonyl, then what happens is the oxygen in the carbonyl then becomes a hydroxyl group. And this is what is called the ring form of glucose. I've written this on the right, and the way that it's written so that it looks like a hexagon is called a Haworth projection. And the stereochemistry of it is properly drawn for a D-glucose, which would be to have the hydroxyl right next to the red hydroxyl. So this would be on the number 2 carbon, would be down, then up, and then down. And then what we see up at top is a hydroxy methyl group, which is up, which always happens in the D sugars. You're not going to have to draw these sugars of the Haworth projection of glucose. I'm not going to expect that of you, but I do want you to be able to identify an alpha or a beta sugar. Now, if you look at the hydroxyl in red, you can see that it is down. When you have that hydroxyl group down, it is called alpha D-glucose. You are not going to have to do this, but I'm just going to show you why it looks like it does in this Haworth projection. So, and how we can figure out that that is actually the way that it should look. If you take the Fisher projection of D-glucose and turn it on its side, you get the molecule having the hydroxyl groups down, up, down. As you can see, the yellow's down, the blue is up, and then the brown is down. It's actually, it loses its chirality this way, but it gives us a simple way of looking at this ring formed, the Haworth projection. You can see that the oxygen that's in red comes around and it's going to attack the carbon of the carbonyl. Okay, and over here on the Haworth projection on the right, you can see the oxygen and then the line going to the carbon now are in red because that's where it's formed. And then the oxygen that was in the carbonyl now has become a hydroxyl. Again, when that hydroxyl group with that is where the other oxygen has attached. So you see this carbon has 2 oxygens on it up here at the right. When that hydroxyl group on that carbon is down, it's called alpha. If the hydroxyl attacks on the other side of the aldehyde group, which you don't really have to understand how this occurs, but when it does attack from the other side, the hydroxyl group there on that carbon with 2 oxygens attached to it will be up. When you have the hydroxyl group up there, then it's called the beta anomer. The alpha form and the beta form are called anomers of glucose. And all that differs between them is whether that hydroxyl group is either up in the beta form or down in the alpha form.
To compare the alpha and beta rings, you can see they are identical everywhere except for that carbon that is attached to the oxygen in the ring and has a hydroxyl group attached to it also. The hydroxyl group is down for the alpha and up for the beta. Fructose will also close a ring, but because it is a ketone, it's going to have one less carbon in that ring, and so it forms a 5-membered ring. If I look at how this happens, you can see I rotate it by 90 degrees again, and then that chiral carbon that makes the D in fructose, you can see that's the bottom chiral carbon, and it has the hydroxyl group on it. That oxygen comes around and attaches to the carbon in the carbonyl and makes the ring closed form. Again, you can see there are going to be, they're attached to that carbon that used to be the carbonyl. You now have that carbonyl changed to a hydroxyl group. And there is a methyl hydroxy group attached to it. It can't go away, but we look at the orientation of the hydroxyl group to determine whether it's alpha or beta. You can see that the alpha fructose has a hydroxyl group down, just like the alpha glucose did, and the beta fructose has a hydroxyl group up, just as the beta glucose did. Ribose is like fructose in that it makes a 5-membered ring. If you look at this, though, instead of being a ketone, it is an aldehyde like glucose, but there's only 5 members to the ring after the oxygen that in the hydroxyl group on the carbon that makes it D. So it's the chiral carbon that is at the bottom. When that oxygen comes around and attaches to the carbon in the carbonyl of the aldehyde group, you get a 5-membered ring. For the beta ribose, the hydroxyl group is up. For the alpha ribose, we get the hydroxyl group down. Notice when we rotate so that the aldehyde group is on the right, that takes the 2 hydroxyl groups that are right and makes them down. And then in the ring closed compound we see they're down. But of course then the carbon that used to be the carbonyl can either be alpha or beta, meaning up or down for the hydroxyl. We're going to see here how a disaccharide can be formed. The disaccharide we're going to look at is maltose. Maltose is formed by the joining of an alpha D-glucose with a beta D-glucose. When these 2 glucoses are joined together, water is removed and they basically make an ether linkage. Now that ether linkage is called a glycosidic linkage. But let's go ahead and take a look at this and examine the molecules and then see how it forms the bond. If we look at the molecule on the left, alpha glucose, you can see that the hydroxyl group right there where the carbon is attached to the oxygen in the ring, it's down. That means it's alpha. The one on the right, the carbon that has both the hydroxyl group and the oxygen in the ring on it has the hydroxyl group up. So that's beta glucose. When I go to join these two, water is going to be removed, and I've highlighted the atoms that are going to come out as water in blue. When they are joined together, you can see that those two hydroxyl groups that were highlighted now have been joined together into that linkage that we call glycosidic linkage. Now this is called an alpha glycosidic linkage because the oxygen that was in the that was part of the hydroxyl group that made it alpha is in this linkage. That's why it's called an alpha glycosidic linkage. The oxygen is down for the carbon that is attached to the oxygen in the ring. Let's look and see how lactose is formed. Lactose is formed by beta galactose and beta glucose, and I'm showing you beta galactose on the left and beta glucose on the right. Now, I haven't shown you the structure of beta galactose before, but you can just accept that that's what it is. Now you can see that the beta galactose has the hydroxyl group on the carbon that has the ring oxygen on it. That hydroxyl group is up. If I look at beta glucose, you can see that the hydroxyl group on the carbon that has the ring oxygen on it, it is also up. But that beta glucose hydroxyl, the hydroxyl group that makes it beta, where it's up, isn't going to participate in this linkage. What we're concerned about is the hydroxyl group that is beta on the galactose and the hydroxyl group that would basically be on the number 4 carbon in the glucose. We're concerned about those two groups because that's where the linkage is going to occur. So if I look at this, I can see that water will be removed so that you get the glycosidic linkage. The glycosidic linkage is going to be up on the galactose. Because it is up on the galactose, we call it a beta glycosidic linkage. Now, you can see it's on the 1 carbon on the galactose and the 4 carbon on the glucose, and so we call it a beta 1,4 glycosidic linkage and all that. I just want you to know that it's a beta linkage when the oxygen that is on the ring carbon that has the oxygen in the ring attached to it, when it's up, then it's going to be a beta glycosidic linkage. If I look at sucrose, you can see that I have alpha glucose on the left and beta fructose on the right. The two hydroxyl groups that are going to join together to make the glycosidic linkage are the ones that I've highlighted in blue, and you can see that the alpha glucose has the hydroxyl group on the carbon that is attached to the ring oxygen. It has the hydroxyl group down, and with beta fructose you can see that same hydroxyl group that is attached to the carbon that is attached to the ring oxygen has the hydroxyl group up. That's beta. When these join together, there's a little bit of twisting the molecule around so that you can see how it's linked, and you can see that the beta is up and the alpha is down on the glucose, and we get what is called an alpha 1 to beta 2 glycosidic linkage, but you can just see that it is a glycosidic linkage.